These are the Chapter 1 Notes 4, Measures of Center and Spread. We're going to first start with this graph on the right side. This is an example of something that's called a time plot, and you'll notice along the horizontal axis we have some different types of time measurements. Time plots will feature time along the horizontal axis, and this time measurement can be anything from seconds to minutes to days to weeks to months to years. The variable of interest will typically be found along the vertical axis, and in the case of the graph on the right side, we're looking at gold prices, and that's the variable we're interested in over a set period of time. When you're creating your own example of a time plot, especially an example like number 1 where we're supposed to graph the following high temperatures over the last 2 weeks, what we're going to do is we're going to graph these values kind of consecutively, one point after the other, and then we're going to connect them with line segments when we're done. Looking at the temperatures here, they kind of span from about 68 degrees to 81 degrees. So we kind of want to make sure that we go as low as probably about 60 and as high as, around 90, I guess. So I'm going to start my vertical axis here at 60. Skip a tick mark. I think I can do that. We'll make this 70, 80, and 90. I'm guessing these are days of the week, but all you have to do is plot this first point, like here at 81. So we'll call that about here. And then we're going to do the same thing for 76, which is our next point. It's probably about here. 69 degrees about there. And we'll just keep moving one space to the right as we plot these points. 68, 72, 75, 77, 78, 79, back down to 74 again, 76, and 78. Once you have these individual points plotted, we're going to connect them with line segments. In the second example, we're going to get away from time plots. We're just going to talk about center and spread for a couple of different cities in the United States, St. Louis, Missouri, and San Francisco, California. St. Louis has temperatures that vary as low as 29 and as high as 79. These are your monthly average temperatures, so it does combine the high and the low temperatures. Obviously, high temperatures in St. Louis in July are going to be warmer than 79, but if you average the daytime high and the overnight low, that's what you'll get. San Francisco doesn't quite get as cold in the winter, only gets down to about 49 degrees, but the average temperature on July day is going to be 62. So if they have a high of about 72 degrees and a low of 52 degrees, it'll average out to 62. When you take a look at the measures of center and spread for these, we can use your calculator, and if you go to Stat, Edit, I've entered the St. Louis, Missouri points in List 1 and the San Francisco points in List 2. I'm going to then hit Stat again, go over one space to Calc, and we're going to look at these one variable stats, starting with the St. Louis data. So I'm going to use second 1 for L1. And the numbers you'll see here, this value that says X bar at the top, that's actually the value for the mean. That's the average temperature in St. Louis throughout the year. So we're going to use a mean of St. Louis of about 55.3 degrees. If you would rather use the median, you can scroll down. There's a little down arrow here. If you hit the down arrow button, you can actually see what the median is. And that's this number 57 down there. For the spread of data, there's a number of different measurements we can use, and we talked about the other day. You can calculate the range, which is the maximum minus the minimum. If you subtract these numbers on the screen, the maximum is 79 minus the minimum of 29. That would give you a range of 50. If you were interested in calculating the IQR, you could subtract Q3 minus Q1. If you took 72.5 minus 38.5, that would be about 34 degrees. Or if you wanted to calculate this value known as the standard deviation, I'm going to scroll up a little bit by pressing the up arrow. And standard deviation is a value that's listed under SX. It says 17.9. That's what we use for that. Now we're probably most familiar with the range. The range tells us that there's a pretty big gap in temperatures between the coldest months of the year, January, and the warmest month of the year, which is July. Now if we do the same information for San Francisco, we're going to go Stat Calc, one var stats again, and I've entered my San Francisco points into List 2. When I calculate this data, you'll notice that the mean is 56.8, which is pretty similar to what we saw in St. Louis. Those temperatures are very similar. If you scroll down your screen, if you wanted to find the median is 56.5. I just noticed I wrote down mean twice here. That should actually say median. So the means and medians between these two cities are very similar. However, when you start looking at measures of spread, like how far apart the maximum and minimum are, for San Francisco, this range is only 15. There's only a 15-degree spread between the warmest month and the coldest month. And even measures that you're probably less familiar with, like the IQR, 61.5 minus 52.5, that's only a spread of 9. And even the standard deviation listed under SX, it says it's 5.39. All these numbers indicate that the spread of the numbers in San Francisco isn't quite what you see in St. Louis. So that does tell us an important part of looking at information. Knowing an average is kind of a big deal, but if you were to say, St. Louis and San Francisco have basically the same average temperature, that only tells you part of the story. There's some major fluctuations in the temperatures of the different seasons in St. Louis compared to San Francisco. San Francisco being close to the ocean, temperatures are a little bit more balanced throughout the year. Even if you take a look geographically at where these cities are located at, it's not too big of a surprise that they'd have the same average temperature because they're more or less directly along the same line of latitude right here. But again, you can see San Francisco is going to be affected climate-wise by the ocean over here. So its winter temperatures aren't going to stay as cold, but likewise its summer temperatures aren't going to stay as warm. So what comment do we want to make about the center and spread between these cities? Probably want to say that basically they have the same mean or median temperatures, or very similar mean and median temperatures, but their spread of their data is considerably different. We're next going to talk about resistant measures, and resistant measures are measures that are not strongly affected by outliers. Imagine right now that we were to take the average age of students in class. We'd probably get about 17 years old because most students in class are probably 16, 17, or 18. As soon as Mr. Herrick walks in the room, all of a sudden the class average spikes up to probably 20 or 21 years old. The mean is considered a non-resistant measure of spread because just adding one outlier dramatically impacts what the mean is. However, if we were to put Mr. Herrick's age at the end of a list of ages of people in the class, it would really not affect the median too much. The median is the number in the middle. It might change from like 17 to 18 or 16 to 17, but it wouldn't jog up as much as adding one old person. Heck, we could add somebody that's 300 years old to class, and it wouldn't affect the median all that much, but you can imagine it would have a big impact on the mean. Similarly, the range is also a non-resistant measure, because right now, if we take the range of students' ages in class, it's probably only 2 or 3 years if you take the oldest age in class minus the youngest for students. As soon as Mr. Herrick walks in the class, all of a sudden the range is around 24. Range is not resistant to outliers. It doesn't hold back, it is dramatically affected. A resistant measure to outliers would be something like the IQR. Big and small numbers at the beginning or end of a list are not impacted by the IQR because if we take Q3 and Q1, they're typically in the middle. Just for future information, standard deviation is also considered a non-resistant measure. Sometimes when you're given a list of numbers, you will be asked to identify what's called the 5-number summary, which consists of the smallest number, the minimum, the largest number, the maximum, the number in the middle, the median, and then kind of the halfway points between the minimum and median, the first quartile, and the halfway point between the median and the maximum, which is the third quartile. So similar to a basketball game or a football game, you have the minimum, the start of the game, the end of the first quarter, the median, that's like halftime, end of the third quarter, and then the maximum is like the end of the game. While your calculator can be used to find the 5-number summary, and pretty easily, in fact, we kind of noticed it earlier today, if you go to Stat and then Calc, you'll find the 5-number summary is listed kind of at the bottom of the OneVar Stat screen. And you can identify the numbers here. If you have a list of numbers like you see for number 3, a quick way to find the 5-number summary is, well, the minimum and maximum are pretty easy to identify. I usually draw a line where the middle is, and if the middle happens to be a single number, that right there is going to be your median. So the median in this case is 3. Once you draw your line in the middle, you'll notice that the smaller half of the list has 2 numbers, and the larger half of the list has 2 numbers. So there's 2 numbers above the line, 2 numbers below the line. If we take the halfway point between the 2 numbers on the small end, this is where your Q1 is at. It's halfway between 1 and 2, so that would be 1.5. If we look at the bottom 2 numbers, this is your Q3. It's halfway between the bottom 2 numbers, so that would be 4.5. And obviously your minimum is going to be this first number, 1, and the maximum is going to be the bottom number, 5. So showing how this works for other examples, if you have an even number of numbers, the halfway point is going to be halfway between 3 and 4. That'd be 3.5, and that's going to be your median. So if the median is made up of 2 numbers, go halfway in between them. If we draw a line where the median is, there's 3 numbers above the line, 3 numbers below. So the halfway point of these smaller 3 numbers, which would be 2, that's your Q1. The halfway point between these 3 numbers is 5, that's your Q3. And obviously the minimum is the smallest number, and the maximum is the largest number. If you have an odd number of numbers, the median is in the middle. In this case, 4. You'll notice again there's 3 numbers above the line, 3 numbers below, so it's easy to pick out Q1. Q3 is the middle of these 3 numbers, that would be 6. Minimum is 1. Maximum is 7. And again, if you have an even number of numbers, 4 numbers above the line, 4 numbers below the line, we'll draw a line right in the middle. That's where your median is, halfway between 4 and 5. 4 numbers above the line, so we'll go halfway between these 4 numbers. That's where Q1 is at. It's like 2.5. Halfway between these numbers, between 6 and 7, is where Q3 is. 6.5. Smallest number is your minimum. Largest number is your maximum. Always be sure when calculating the 5-number summary to put the numbers in numerical order. So if you see a list like the list we had earlier today with the temperatures of St. Louis, these temperatures are not in numerical order. So the first thing you'd want to do is order them from smallest to largest. Then you can identify the 5-number summary. The last thing we're going to look at today is something called weighted averages. Here's a particular question. One class of 40 students had an average score on the last test of 78 points. Another class of 30 students had an average score on the last test of 70 points. If we were to combine the classes, what would the average score on the last test for all students be? Well, it's not quite as easy as averaging 70 and 78 and getting 74. The reason is that one class has more students, so that's going to be weighted a little bit more heavily. So how do we figure out what this overall average is by combining 2 classes of unequal sizes? Well, if the average score on the first class of 40 students is 78, imagine that every student in this class scored 78. If you wanted to find the total points for this class, what you could do is you could take 78 points times the 40 students, and this would give you the total number of points earned by this class. So if we calculate 78 times 40, that gives us an answer of 3,120. Now that's for the first class. For the second class, same idea. They average 70, but there's 30 kids in class. So if you wanted to figure out the total points they earned, imagine each kid earned 70 points. That would give you a total of 70 times 30, and that's just equal to 2,100 points altogether. So the total number of points from everybody in the first class was 3,120. In the second class, it was 2,100. This gives you a total number of points of 5,220. This is the total number of points between the 2 classes. Now, if we add up the total number of kids between these classes, there's 40 in the one class and 30 in the other. That's 70 kids total. And if we were to combine the classes, all we have to do is take the points earned by everybody in these classes divided by the total number of kids. And we would expect that if you divide 5,220 by 70, we should get something probably closer to 78 than 70 because the one class has more kids. It's going to be weighted a little bit more heavily toward that class. And when we divide this out, we do get 74.6 approximately, which is slightly closer to 78 than it is 70. And that's a way to calculate a weighted average. So today what we've talked about today is kind of working backwards. Weighted averages, 5-number summaries, types of resistant and non-resistant measures of center and spread, and the importance of analyzing both center and spread when looking at data. We began class by talking about a time plot, And that takes care of our Chapter 1 notes floor.